Okay, hello everybody and welcome to this lecture, lecture 7, part 2. This is where we bring this part of the course to a finish. We discuss Weyl's theorem. That's the main point of this lecture. What is Weyl's theorem? Well, it discusses the representations of finite dimensional representations of semi-simple Lie algebras. So we know by our previous work that a semi-simple Lie algebra is a Lie algebra that decomposes into a direct sum of simple Lie algebras. Okay. What Weyl's theorem says is that if you look at any representation of Lie algebra, that representation necessarily decomposes into a direct sum of simple sub-representations. So it's quite a powerful result. Saying once you start with a semi-simple Lie algebra, that automatically forces all of the representations to behave in a similar way, to also be constructible from these building blocks, these simple representations, these atoms of the representation theory. Of course, it goes the other way as well, because you can always represent Lie algebra on itself by the adjoint representation. But it says so that the collection of all representations, basically, are finite dimensional, of course, representations, has this very nice structure. It can be built out of these atoms. So that's Weyl's theorem. To do so, we need to introduce a powerful tool in Lie theory known as the Casimir of Representation. So let's start off. Let sigma from L cross L to K be a symmetric, non-degenerate L-invariant form. Okay, just similar, just as we've been using in many results, theorems, constructions, and so on in previous lectures. Now, what we're going to do is choose a basis of our Lie algebra, x sub 1, x sub 2, x the n, and then we're going to take a dual basis, y sub 1, y sub k. So remember, for something like an inner product, because it's positive definite, the dual basis and the basis coincide. x1 pairs with x1 and kills everything else, x2 with x2 and kills everything else, and so on. Here, we're not assuming, we're not dealing with inner products. We're dealing with things which are non-degenerate, not positive definite. So the element that x sub y, there will always be an element that x sub 1, for example, pairs with to give a non-zero element, to give a non-zero scalar. But that's not guaranteed to be x1 itself. It could be another element. So in general, you have two bases that you will pair, and they satisfy this condition. Okay. This with respect to the Kronecker delta sigma. Okay, so let's do that. We choose a basis, take a dual basis, and then we use this dual basis to define the Casimir operator. So this is an operator that goes from the representation to the representation. How does it work? It acts on any element V as multiplication. Well, so just to be sure what's going on here, I guess we should really have a bracket here to be more careful. But we operate yi on V, and then we operate xi on V. This makes sense because these are contained in the Lie algebra, and we have a representation, so we can let the algebra act on V. And then we do this for all i's in the basis. Oops, sorry, that should be an n. It's a typo. For all elements, and sum them up. And this is what's called the Casimir operator. So I guess the first question you ask here, this seems a little bit artificial. We're using a basis to define an operator. In general, that's if the choice of operator you have depends upon a choice of basis, then it's not a very canonical operator. It's sort of artificial. So looking at it at first glance, the Casimir operator would seem to be a sort of an artificial construction. However, as we'll now show, the Casimir operator is actually independent of the choice of basis. We need to choose a basis in order to define it, but that choice of basis doesn't actually matter. So therefore, we see actually it is kind of a canonical natural operator to consider, because this choice of basis doesn't matter. What's also very important about it is that it's actually a homomorphism of L modules. So it's going to commute with the action of the representation. And that's an extremely useful property. Okay, so let's show that the Casimir operator is independent of the choice of basis. We'll let x prime sub I be another basis, and y prime sub I be the dual basis of L with respect to sigma. And then we'll define two matrices, A and B, such that they're change of basis matrices, basically, such that we can express basis element x prime sub k in terms of linear combination of these guys. Okay. So basis. Just note how so the k is to here and the I is the one that we're summing over here. Choosing another basis, B, we have y prime sub L is going to be expressible in terms of the original dual basis y sub j. Here, notice the j is first and the L is second, so it's switched. It's just convenient to do it this way, okay? Then it holds that. Let's basically take our defining property for the dual basis, this Kronecker delta property. It's going to be 0 unless k is equal to L. And then expand this using these here. So this is just substituting in. So we're going to take this and we substitute it in here. Let's take out the summation. We're summing over I and j. So the A is going to go here, and then we've got the xi's. They've changed from an x prime to an xi at the cost of this summation. Similarly, for the second entry, we're taking this here. We take the scalar out, the b, we leave the y sub j inside there, and then we're summing over I and j is equal from 1 to the n. But now we know that the first basis we chose was a pair of dual bases. So this guy here is going to be Kronecker delta again. It will be non-zero if and only if I is equal to j, whereupon it's equal to 1. So basically the I and the j here, you see, corresponding to the I and the j over here, they're just going to collapse down, and we're going to get a summation over I. So I must be equal to j, so we get an I and an I here. But what is this? Well, this is just matrix multiplication. It's the coordinate KL in the product of the matrix A and B. It's the matrix entry of the product. Just usual matrix multiplication that you all know very well. So what does this mean? This means that the entry here in this matrix KL, the entry is actually always going to be equal to Kronecker delta KL. But that's just the identity matrix. It's just going to give you ones in the diagonal and then zeros everywhere. It's the identity. That, of course, by basic matrix manipulation, equivalently means that BA is equal to the identity. So this is the one that we prove, and then actually it turns out we need this, but of course it's equivalent. Okay. So continuing. Sorry, it should not be, so continue, that 3 should not be there. Now, so looking now at this quantity here, so this is the Casimir, okay? This is the operator that gives you the Casimir. I'm not putting in the V here just so that I can fit everything in one line. Of course, the product here doesn't make sense because it's inside in the Lie algebra and there's no multiplication. So just by abuse of notation, I guess I've not written the V here upon which it's acting. I guess to be more careful, one should. Okay, so this sum here, let's now express that using the matrices A and B that we had before. We can re-express this sum, and it becomes, of course, I and j summing over k. We brought out the summation of I and j, and this is ki, because it was the k was first here, and then the I for the A, and then bj, k went second in our conventions here, and we have the j. We sum over this. And of course, we've got the I here, and we've got the j here. Okay. But now, what's this? Well, you see, this is now equal to the matrix multiplication. So we can just switch the two of these around. I mean, they're the scalars, we can switch these around. And when we switch them around, we see that we've got matrix multiplication for the matrix BA. It's the jith coordinate. So it's the first and the last coincide. So that means that the order here of the BA is going to be switched. Nothing too difficult going on there. And it's going to be the I and the jth entry. Once again, we're summing over k. So that tells us this. But remember from the previous line, we showed that BA was actually equal to the identity. So that means that this coefficient here is going to be 0 if I is not equal to j, and when I is equal to j, it's just going to give us 1. So this basically, the j and this disappear, and we just get the summation here. And what's that? That's the Casimir with respect to the other bases. So we see that the Casimir operators actually coincide. Okay, so that's the proof. Nothing complicated going on, just some tricks with matrix multiplication. So let's now move on to the second part. Let's recall what the second part actually was. The second part was that the Casimir operator is a homomorphism of L modules. Okay, so for any x contained in L, we let x sub k and x, we're going to denote, we're going to expand them in terms of the basis here. I mean, of course, this is an element of the Lie algebra. Okay, so it's the Lie bracket of these two elements here. And of course, any element in the Lie algebra is expressible as a linear combination of the basis, and these are the coefficients. So maybe to be completely clear, this should really be a colon here to say that this is just introduction and notation. And over here, it's exactly the same thing, and we're going to denote we're going to take x and yl, we're going to expand it, and then we're going to express it as a linear combination of the dual basis and the coefficients here, b by j. Okay. Note the slightly different conventions here. Here, the second index is going to match with the index of x, and here it's the first index matches with y. Just turns out to be a useful convention. So what does that mean? Well, it means that we'd now like to learn something about these coefficients, or in fact, the relationship between these two coefficients. So we have alpha k sub L is equal to sigma of x sub k sub L. Okay, so we see that this is, why is this the case? Well, look, we've expanded this. Take the expression for x sub k up here. Okay, it's this guy. But we know that these were dual bases. So the only, out of this summand here, out of the summation here, the only thing that y sub L is going to pair with is going to be the L. Okay, which is to say with this guy here, which means that this is the only coefficient that remains, and it's precisely this. Okay. So all of the other summation, all of the other the summands, except for I is equal to L, all of these summands will be killed when you pair them with y. If you don't pair them with y, you're going to be left with this coefficient here, alpha k sub kl, which we take out, the k sub L, and then we're left with xlyl, which of course goes to 1. Now, we assumed at the start, remember, that this symmetric bilinear form is L invariant. That means that we can bring the Lie bracket, or we can bring the Lie bracket to the other side somehow. I mean, this is precisely the definition of L invariance. So we're left with xk, and we're left with the product here. But no, exactly the same thing happens. So we take this, we take this and substitute it in to here. Then, of course, the x sub k is only going to pair with the y sub k in this summation. So we're going to be left with the coefficient k sub L. Okay, will only pair with this when it will only give you a non-zero pairing when k is equal to j. So that means that the coefficient is going to be beta k L, and that's what we get out here. So we see that the coefficients match. So for these two matrices, the coefficients match, which means the matrices are the same. So L invariance tells us that the matrices are the same. So let's now use that. We want to show that this is 0. So we want to show that when our Casimir operator, so yes, sorry, you see here I've dropped the V. So this is sort of a convention. People get sick of writing the V when, of course, it's clear what representation you're. So we use both symbols. When it's clear which V is being acted upon, then we usually drop the V. So it's more convenient. So if we let C sub sigma act on xv, we want it to be equal to, we want to be able to bring out the x. That's what it means for it to be an L module map. All right. So let's show that this is equal to 0. Let's expand it out using use the identities that we've proved before. And hopefully upon rearranging everything will cancel. That's the plan. So what is the Casimir? Well, first is we put in, I mean, we know the Casimir is going to be the summation for x sub k, y sub k acting on, and the x is here. Remember, the x is still there, so we're letting the Casimir act on this guy. This is the x. We've brought out the v, we've collected the terms together, and this is the term coming from the Casimir. Okay. Same thing over here. This is the term coming from the Casimir. And the x is coming from over here. So in when you expand it out explicitly in terms of the basis, this is the difference between the two terms. In this one, the x is at the start, and this one, the x is in the middle. And I guess we somehow want to be able to either bring the x's through here so that these things cancel, or bring this x back here so that these two things cancel. That's the hope. So what do we do? We're going to write it like this as a commutator. So remember that this product, it's not a product inside in the Lie algebra. Here, we're again by abusive notation, we're not explicitly denoting the representation, but we're now viewing these elements as living inside in the endomorphism ring of the representation, V. Okay, so this is really just matrix multiplication. Remember, a representation is going to be a Lie algebra map from your Lie algebra into the general linear group of the representation. So you're going from an abstract Lie algebra into a concrete Lie algebra where the Lie bracket is just commutators. So now we're going to use the fact that it's a commutator to do this expression. So we see this gives us x. If we look at the first term in the commutator, it would be x sub k, y sub k by x, and then minus x sub k, y sub k, x. Over here, the first term is going to be x sub k, x, y k, but that's going to cancel with this guy here. Okay, because in the second term, these have been reversed, and we have a negative sign. So this guy and the extra term cancel here, and the last term that's left over here is just going to be this one here. It's going to be minus because we've reversed it, and then we've got the x sub k and the y sub k, and that's exactly what's here. Sorry. So we've re-expressed this in a commutator. So we've re-expressed this in commutator form, just using the simple cancellation. And then what we do next is we recall the expansion of this commutator in terms of the basis y. Okay, so that's where now we've got a summation over I and k, and this extra term has appeared here, and this is the coefficient. So the x is the same. Nothing happens to the x up here. It's this thing that we're changing. We're changing it into this summation. We brought the coefficient in front, and we left the summation over the yi here. Same thing happens over here. The yi doesn't change, same yi here, yk, sorry, and the same yk here. And then this guy is the summation here. Okay, just as we showed on the previous slide. Why don't we just go back for 1 second? Remember, just using these expressions here. Using these expressions to expand out the commutator bracket. But what we know from before, now look at this. What do we have when we've done this? We've got a summation over xky, and we've got a summation over xi, yk. The fact that we have different coefficients here, the fact that we have different indexes, I should say, doesn't do anything, obviously. It's just a finite summation, so that this won't change. It's just going to be a switch the symbols. So basically, it's the only thing that stops these two from being different is that the coefficients are different. But as we saw above, the coefficients of these two matrices are actually the same. So the coefficients are the same. So it turns out that this thing is actually equal to 0. Also, there's a minus sign here. Maybe I didn't mention that because there was the switch. If you look up here, we had x. The x was second, and here it's first. And yeah, it's switched around. So here it's yx, here it's xy, here it's xx, x sub k, x. Here it's, yeah. Okay, next second. So that means that they vanish. Sorry, there's a sign error here. Yeah, that's what's happened. Because the x sub kx is the same. Yes. It's this much. So the minus should be in here. Sorry, that's the typo. That's why I was getting confused. Okay. But anyway, they vanish, which means that this thing is actually equal as we claimed it would be. Hence, the thing is a Lie algebra homomorphism. And we're done. Okay. So let's just go back, because there was a lot of technical argument there. what have we done? We've basically identified this canonical operator, the Casimir operator, introduced in terms of a choice of basis, but then shown that it was independent of the choice of basis. And why are we interested in it? Well, we're interested in it because it's a very useful way of producing an L module map. That's the essential property of the Casimir that we're interested in. That it's a way of producing L module maps. When we have remember the assumption was that we have a symmetric non-degenerate L invariant form. And as we know, the existence of these things is subtle. It can depend on what type of Lie algebra we have, so we're not always guaranteed to have these Casimir. Now, let's look at a further property of the Casimir under some assumptions. So now we assume that L is a semi-simple Lie algebra. We didn't assume this before. And we want L to be a faithful representation. Then the bilinear form, sigma, will go from L cross L to K, given by the representation as usual. It's the same way that the same trick we've been using all along to construct bilinear forms from representations, just by taking the trace of the product of the two things. This is non-degenerate. Okay. And you should try to compare this to remember or get into your heads the previous results we did and the relationship between semi-simplicity and non-degeneracy and so on. So look back to the previous lectures and see how this one compares. We won't go into it here. The important thing is that when you have a faithful representation, semi-simple Lie algebra, you get a non-degenerate form. And second, the associated Casimir operator. So we know that this is L invariant. So we know that we have, we know it's L invariant and we know that it's symmetric. So together with non-degeneracy, that implies that we do actually have a Casimir. And what does this Casimir satisfy? Well, it's the trace of the Casimir. Remember, the Casimir is going to be a linear operator on a finite dimensional vector space, so we can consider its trace. The trace is going to be the same as the dimension of the Lie algebra. All right. So you see here that this is independent of the choice of representation and even the choice of the bilinear form. So this is somehow a constraint. No matter what representation or what bilinear form you choose, the trace of the Casimir will always be the same if your Lie algebra is semi-simple. Okay. So let's prove that. So let's just, for simplicity, because it's an injective representation, we can assume without loss of generality that L is contained inside the general linear group of B. So if we consider the ideal I, which is going to be, again, as usual, we're taking the elements inside in L that are perpendicular, I guess, with respect to every other element inside there. So we're trying to show non-degeneracy. So it's things like this. It's things in this ideal I that actually stop, or that break, that the existence of such elements is equivalent to degeneracy of the bilinear form. So we want to look at this ideal and then basically show that it's zero, and hence conclude that it's non-degenerate. This ideal I is contained inside the general linear group of V, so we can consider, and the trace of any two elements contained inside in this ideal I is going to be zero. Okay, by definition of the ideal. But remember back to the Cartan criteria for Cartan's condition. This implies that I is solvable. But L is semi-simple, therefore it has no solvable ideals by definition. It's the equivalent definition of semi-simplicity. Hence, that means that the ideal must be I, and therefore it's not degenerate. Okay, so not such difficult argument. It's reminiscent of similar arguments we had done in previous lectures. Let's now move on to the trace of the Casimir operator. Well, the dual basis, x sub I and y sub I, they satisfy the trace of these two, which is equal to sigma by definition of sigma. But that's equal to Kronecker ij because they're a dual basis. And that means that the Casimir is going to satisfy the trace of the Casimir is going to be equal to the trace of these elements here, which is equal to Kronecker of ij, which is equal to the dimension of. Okay, so it's the non-degeneracy allows us to choose a dual basis, and then to define the Casimir, and then the property of this dual basis. We see easily that the trace of this thing is just going to be equal to the dimension. Right, so a simple argument. Let's go back to what it is, but a powerful one as we'll see below. Now, this is a technical lemma. It's a long lemma. It uses the two tools that we introduced before. It uses the Casimir and then the results that we had about the Casimir. And with this result, this is going to be basically the workhorse. With this result proving Weyl's theorem, the fact that every representation decomposes into a direct sum of simples will be relatively easy. It's in this lemma that we do the hard work. Okay, so let's read the lemma and see what it states first of all. So if we have any L representation V, any L module, then it claims that we can decompose it into LV, L sub V, and a direct sum of L of V. This is just the image of V into the action of the algebra, the span with all elements of the form X, V, small x, small v, where X is in L and V is in V. What does this mean? Remember, we defined this a long time ago. This is just going to be equal to the elements V, this V contained in V, such that X V is equal to 0 for all X in L. Okay, they're the elements that are killed by everything in the Lie algebra L. And what this is saying is that basically, yeah, you get this canonical decomposition of any representation for a semi-simple Lie algebra. You get a canonical decomposition of any Lie algebra into the 0 parts and L of V. Seems reasonable, but proving it takes some work. And the second part is that for any surjective homomorphism, this is actually an easy consequence. The hard work is up here. The hard work is in this. Once you have this, we'll see that the second part is not so difficult. It just says that with respect to this decomposition, any surjective homomorphism from V to W here is going to be another L module, another representation of L. Then it always brings the elements in V to the L, which are going to be killed by L. It maps them onto all the elements in W that are killed by every element of the Lie algebra L. And it's surjective. So if you find any element inside in W that's going to be killed by all of the L's, that will be equal to the image of some element in V killed by all of the L's under your surjective homomorphism. But as I said, it's this guy here, it's the first one. That's where the work is involved. This one we'll get kind of easily. Okay, so let's start. If V to the L is equal to V, which is to say everything inside and the representation is killed, which is to say that it's basically just a 0 representation, then it happens that then of course LV is equal to 0. That's clear, and then the statement is obvious. So in the case where you've got this trivial 0 representation, then the statement is obvious. Why do we labor in that? Well, that means that we can now assume that the representation is not 0, which is to say there will be elements. We now move on to the other situation where this is not the case, which is to say the case where there are elements contained inside of V which are not killed by the representation. So we assume that these two are not equal, that this is properly contained inside of V. Okay, so this would imply that the following representation is non-zero, clearly. The image of rho inside in G of L is again a semi-simple Lie algebra. You should think about that for a second. Think about the fact that we can decompose any Lie algebra into a direct sum of simple Lie algebras. And then the Lie algebra, let it operate on each part of the simple. the kernel of rho restricted to any simple Lie algebra will be it will be an ideal inside there. Hence, it has to be 0 over everything. So basically, when you've decomposed it into simples, you've decomposed L into simples. Rho basically either maps every sum and every simple part injectively into GL of V, or it kills it. Okay, so it's either in or out, but it doesn't. Again, these things are somehow like atoms. These simple components, these simple summands. So it either has to get rid of them, or it just transfers them in directly, which is to say it gives an injective map. Hence, the image of it is just going to be some of those simple ideals which these simple ideals which were not killed. Hence, the thing is semi-simple. Okay. Okay, so moving on to the next slide, we see that note from the previous lemma. So this row of L that we have, this row of L lives inside in GL of L. So it's, I guess, the identity is basically a representation of row of L, and obviously a faithful representation. The identity is an injective map. And as we said before in the previous slide, row of L is semi-simple. It's made up of a direct sum of simples. So from the previous lemma, that means we've got an injective, faithful representation of a semi-simple Lie algebra. Hence, that means that the bilinear form coming from the trace, or the trace and the identity representation, this is non-degenerate. But if we've got a non-degenerate representation, and of course the trace is going to give us a symmetric L invariant bilinear form, that means we have a corresponding Casimir operator V. So the Casimir operator is going to be a linear operator acting on V. And taking its Jordan normal form, let the lambdas be the eigenvalues. So with the Jordan normal form, we're going to take, we've got lambdas along the diagonal, our eigenvalues ones above it. We'll go and we take these distinct eigenvalues and let the m sub i's be the multiplicities. Now, we can now consider, okay, so let's just go directly here. Let's now consider the generalized eigenspaces, okay? As you would as usual, so it's going to be the kernel, sorry, there's a typo, something missing here. A note, of course, the m I should be here. No, that's not how it should work. The m sub I should be here. And these will give you generalized eigenspaces. And moreover, it will give you a decomposition of the vector space. Just usual theory of Jordan normal forms that you would know from your first year algebra. But what's important about this, why are we decomposing them into these eigenspaces? Well, the eigenspaces are not so important. The generalized eigenspaces are not so important. The important part is that because C is an L module map, and because the identity is clearly an L module map, this sum here is going to be an L module map. And that means that the eigenvalues, these generalized eigenspaces are themselves going to be module maps. So what we have is we've used the Casimir operator to produce a decomposition of V into submodules. Okay. And now, once we've decomposed it into submodules, we'll adopt, as we many times before, we're going to adopt some sort of inductive argument. So let's assume that the theorem holds for all modules of dimensions strictly less than the dimension of V. All right. Then if k is greater than 1, that means that we've got at least 2 summands inside here. And that means that the dimension of each V of I has to be strictly less than the dimension of V. That means that V sub I lives inside and is in the realm of the assumption. It means that the dimension is such that we've assumed that it decomposes. And this holds for all of the VIs because because there's more than one of them, all of them will have to have dimensions strictly less than the dimension of V. So that means we can decompose all of them like this. And then all we need to do is add all of these things together, and we add together all of these for all I, and we add together all of these for all of the I. And we get the first part of the proposition. Or was it the lemma? It's a lemma, sorry. You get the first part of the lemma. That's if K is greater than 1. Okay. Now, the next, the other situation, the remaining situation that we need to consider is the situation where K is equal to 1, which is to say we've just got one generalized eigenspace, single generalized eigenspace. Then we can't use the induction hypothesis because I haven't decomposed it into smaller parts. We've just got one block. So what do we do in that case? Well, that's where the trace comes in. Okay, so then if K is equal to 1, then by the above lemma, we know that the trace is equal to the dimension. Okay, remember that no matter what the representation of the Lie algebra was, no matter what the dimension of the representation was, or what the bilinear form was, the trace of the associated Casimir was always equal to the dimension of the Lie algebra itself. All right. So this is true, and of course it's non-zero because by assumption the representation was not zero. Therefore, there has to be some of the simple summons in L will have to not be killed. So this is non-zero, but we see that the trace is actually equal to this. We've only got one eigenvalue. We've got a generalized eigenvalue. Look at it in Jordan normal form. And you see, what's the trace? It's just going to be the diagonal. It's going to be the sum of all of the things in the diagonal. But for the diagonal, they're all lambda ones. It's just one eigenvalue, one generalized eigenspace. So it's just the dimension of the representation V, the dimension of the matrix. Now, we know that the representation is non-trivial, by assumption, of course. If it's the zero representation, then it's already taken care of. So that means that lambda 1 is not zero. And it also means that C is invertible. Okay, because it's just a matrix with lambda 1 along the diagonal, zeros below, and then 1's above. So if you take the determinant of this, you're just going to get a product of it's lambda 1 to the power of the dimension of V. So that's non-zero. So that means we've got an invertible matrix, means the operator is invertible. And then from this, it means that if you've got an invertible matrix, of course, it can't have a kernel. And from this, we see that the elements that are killed by every element of L. So see, this Casimir operator doesn't kill anything because it's invertible. But if you have an element that's killed by every element in the Lie algebra, then it would have to be killed by the Casimir. Because of course the Casimir is just coming from, it's a sum of products of elements of the Lie algebra. So that would contradict it. So we're forced to conclude that, in fact, the elements killed by every element of the Lie algebra, V sup L, are actually equal to 0. And of course, we see that the image, well, what the image is equal to V. Because, of course, since it's an invertible operator, it has to preserve dimension. So the dimension of V will be equal to V. Everything is finite dimensional, so it has to give you everything. Hence, we see that, oh, sorry, the M is still there. Let me get rid of that. Hence, we see trivially that it's equal to this, because of course this is 0. Okay, so that's the. Let's go back up to the statement. Let's get rid of this to here. We've now proved this. now prove that we have this decomposition into the elements killed by every element of the Lie algebra and the image of the representation under every element of the Lie algebra. And I said that once we had this, the second part would be easy, that it's going to bring V sub L to W sub L for any surjective Lie algebra Lie module homomorphism. Is that the case? Well, see, for the second statement, we just note that homomorphism from V to W, a Lie algebra homomorphism, it must map V sub L to W sub L. All right? Because it's a Lie algebra homomorphism. It's a simple exercise. And that case, so in that case, because of the decomposition then, so it maps, I guess, it maps VL into here. And it maps L of V into L of W. It now follows from the decomposition that the induced map is surjective. Okay. So I guess, is there anything tricky there? No, not really. I mean, it's basically we're using, so let me summarize, maybe I didn't explain that so well. What we're saying is that V sub L maps into W sub L. And this maps into here. So if this was not surjective, if this map here was not surjective, then because the map that we started with is surjective, then there would exist elements inside here that are still covered, but they can't be covered by an element in here. But that means they have to be covered by an element inside here. But that can't happen because the LV maps into here. Therefore, we have to conclude that this map is surjective. This map is also surjective, but that's less interesting. Okay. So as I said, that is the worst part of that's where we do the hard work for proving Weyl. This lemma is where we put in the hard work. Now that that's done, the proof of Weyl decomposition is actually not that bad. So let L be a semi-simple Lie algebra, then any representation of L is again semi-simple. Okay. That's what I've been saying a number of times since the beginning of the lecture. That semi-simplicity of your Lie algebra, the fact that your Lie algebra decomposes into a direct sum of simple subalgebras, implies that any representation behaves analogously, that any representation decomposes into semi-simple parts into these atoms, which is very nice. Okay, so what are we going to do? Remember, we had a couple of different characterizations of whether a representation was semi-simple. And one of them was that we don't need to actually decompose everyone into these simples. We just needed to show, remember we showed that it was equivalent to the fact that any sub-representation had a complement. That's equivalent. And in fact, of course, that's usually easier to show, and that's what we're going to try to show here. So let V and W be a sub-representation. This induces a surjective map from, these are just linear maps here, okay? Not L modular maps, that's why we have the K. So we're just looking at linear maps from V to W. Okay, so from the larger space to the subspace. And here we're just looking at maps from the subspace to itself, linear maps. Sorry, I forgot the K here. It should be, let me write that in. These are again linear maps. All right. And what is the map from here to here? It's just restriction. So we restrict the domain of the map F to the subspace W. That's it. And clearly this is going to be surjective because you can extend any linear map, just an elementary basis argument. For modules and so on, module maps, that would be very different. But this is just a question about vector spaces. So of course you can extend a vector space, a linear map from here to here can of course be extended to a map from V to W. So that means that this map is definitely surjective. Now, these maps, whenever you have homomorphisms from a Lie algebra to a Lie algebra, so far here, this construction sees nothing of the Lie algebra, the L module structure of V and W. But we can actually use the L module structure of V and W to give these things the structure of L representations. How is that defined? It's defined by XFV. So this is our element. This is as, maybe I should really write this as, well, no, it's okay. So this is X by F. What does this symbol mean? Well, we give it a meaning by seeing how it acts on any element of V. What does it do? Well, here, this multiplication. So in this case, the F by V is an element of W. So any element of W can be acted upon by an element of the Lie algebra L because it's a representation. So this acting on this makes sense. On the other side, we could instead have multiplied beforehand. So X acting on V also makes sense because V lives inside a big V, which is a representation. And then we can act upon this new element inside in V by F. And it's the difference between the two of these things that gives us a representation. So you should check that. And the map phi, check, is actually a homomorphism with respect to this. So you should think about that. It's a nice exercise to, I guess, become comfortable with this definition here. But phi, the restriction is actually is a homomorphism. It's a pretty formal calculation, but a good one to do. But if we've got a homomorphism between these two Hom spaces considered as L module maps, that means that the Hom VW sup L is mapped surjectively onto Hom WW sup L. That was the second part of the previous lemma. But what does this look like in this? So, in general, of course, we know what it is. It's going to be all of those elements inside in Hom VW that are killed by every element of L. But what does that actually mean in this specific case, where we have a concrete description of this module? Well, it's actually going to be all of those elements, F to W, that are L invariant. Okay, that means that the F comes through. So you should also check this. That's another good exercise. Okay, but it is indeed true. That means that any such F, any element contained inside here, will actually be a homomorphism of L modules. Okay, so we've somehow identified inside here, these are just linear maps going from V to W. But by putting the L up here, we've identified those maps which are actually L module maps. So this is kind of nice. You show, you've got your linear maps and you've got an alternative characterization of those maps which are L invariant, which are L module maps, in terms of this sup L, in terms of this new L module structure that we put on the homomorphism space. Now that means then that by surjectivity of F, surjectivity of phi, surjectivity of phi from here to here, we can find an F in the Hom space. We can find an F in this space such that F restricts to the identity. Okay, the identity is definitely an L module map. We know, so hence this identity function lives inside here. But because of surjectivity, that means that there exists a function here that restricts to it. So what we've basically done more down to earth terms is we've lifted the identity function from W, we've expanded it up to a function on the whole space. But this function is again in, it's special, it's not just any linear map because that would be easy. but it's a linear map inside in this space here, which is to say it's an L module map. So we've extended the identity up to an L module map on the whole space. All right. And then we know that V is just going to be equal to W plus the kernel of F. And because F is an L module map, this is going to be a complement. And this means that V is semi-simple. We've shown that an arbitrary submodule W has got a complement. We can find a direct, or we can find a partner such that it sums to give you the whole space. This is a decomposition of modules. And that is an equivalent condition for semi-simplicity of the representations. And that's it. That's Weyl's theorem done. Okay, so this is an important theorem. As you can see, the proof is there's a lot in there, especially building up. We've used Casimir operators, then we've taken the Casimir operators and used them to prove this technical lemma before about mapping L invariant subspace or V sub sup L to W sup L. And then using that, we managed to produce complement for any subspace inside there and hence conclude that it's semi-simple. So a lot of material inside there, but again, the prerequisites are just linear algebra. All right, so let's see if we can find some nice corollaries of this. Well, a corollary is an important consequence is that the following are equivalent. So we have a reductive Lie algebra. So actually, before I start this, remember that we had our abstract definition of a semi-simple Lie algebra, and then we showed that it was equivalent to maybe the more intuitive idea that it was a direct sum of simples. Reductive, we never found something analogous, but now with Weyl's theorem in our hand, we're going to prove something analogous, and that's that if it's reductive if and only if it decomposes into a direct sum of simples, which is to say a semi-simple plus the center. So that's maybe clarifies the relationship between reductivity and semi-simplicity. Any reductive Lie algebra is just a semi-simple Lie algebra together with an abelian. And that's what reductive means. So let's just read through the list more formally. Following are equivalent. L is reductive. The adjoint representation of L is a direct sum of simple representations. And as a Lie algebra, L is a direct sum of its center and a semi-simple Lie algebra. All right, so let's prove it. Okay, so let's consider the adjoint representation going from L into the general linear group of L, as we have many times before. Again, we know that the kernel of this is going to be the center of the Lie algebra. So we can consider L as a representation, as carrying a representation of M, which is to say L quotiented by the center. Again, this is going to be a Lie algebra. And we see that we've got it's in fact a faithful representation here. We also have that since the center in this case is equal to the radical, we see that M is going to be semi-simple. Okay, but if it's semi-simple, that means that L carries a representation. L is carrying a representation of semi-simple modules. So by Weyl's theorem that we just proved, that means that L decomposes into a direct sum of simple M modules. Okay. So if you're a little confused by this about the radical and Z, just go back. It's maybe good revision to go back and remember your definitions. Go back to the definition of what a simple Lie algebra is, a semi-simple Lie algebra, and a reductive Lie algebra. You'll see that this is where this is coming from. Sorry, the K here should be, we should get rid of it. So clear. Okay, so that's the first part. Reductive implies that the adjoint representation of L is a direct sum of simple representations. Just a simple trick and applying Weyl's theorem. 2 implying 3 is a little more difficult. Not that much. So let L be equal to, sorry, this here should be I. So let L decompose, let this be decomposition into simple modules. We can do this because L is by assumption. So yeah, into its simple modules by assumption 2, this is what we can do. Then each K considered as an algebra, as a Lie algebra, does not contain any non-trivial ideals. Okay. However, IK is either simple or abelian. So if it's abelian, then we know that the Lie bracket of L and I sub k is equal to the Lie bracket of I sub k and I sub k, which is equal to 0. And hence that I sub k is contained in the center. Okay. The second identity here is just because of the fact that it's an ideal. And this implies that we can decompose L into a direct sum of I and J, where I is contained in the center and J is semi-simple. But the algebra L, quotient by I, is isomorphic to J, is semi-simple. Hence, I is going to be the maximal solvable ideal. This implies that I is equal to the center, which is equal to the radical. And so we see that L is equal to the center plus J. And that's it. So we've now shown that for any reductively algebra, it decomposes an equivalent. Well, okay, we haven't done the equivalence yet, but we've shown that any reductively algebra can be decomposed into its center and a semi-simple part. So to finish off, show that it's equivalent, actually, we need to do one last part, 3 going to 1. So let's get rid of the clear drawings. So let's now finish it off and go from 3 to 1. Just to say, if we have something that's a direct sum of a semi-simple and its center, then that Lie algebra must be reductive. So our assumption implies that L over Z of L is a semi-simple Lie algebra. Hence, Z is the maximal solvable ideal. And hence, Z is equal to the radical. And that's what reductive means. So we've shown that we have this sort of abstract characterization. So just like semi-simple Lie algebras, or even extending the situation for semi-simple Lie algebras, we have this abstract formulation of reductive Lie algebras. And equivalently, we have, which is as we have here, that the center is equal to the radical. But we now also have this idea, this equivalent picture, that it means that any reductive, it's reductive if and only if it's a direct sum of a simple and the center, an abelian. So it's basically just a semi-simple Lie algebra with an abelian algebra added on. That's it. Okay, so that's good. That kind of brings us, so this result here sort of brings us to the finish of this part of the course, which was all of these discussions of reductivity, of simplicity, reductivity, and semi-simplicity, and how they all relate to each other, and the various consequences, and so on and so on. In particular, one of the high points, Weyl's theorem that we just proved. Now, to finish off, there are a number of results we'd like to be able to prove, but they're either too advanced for a course at this level, or simply we just don't have time. There's really so many nice results in Lie theory that it's impossible to prove everything that you would like to prove. So I'll just finish this part with stating 2 very important theorems that also are a nice way to round off, to finish off this part of the course. And hopefully we'll, even though we don't prove them, we'll give you some insight and some bigger picture as to what's going on with Lie theory and help you to understand a lot of the stuff that we've been doing before. So in order to do this, though, the first theorem we're going to state is Levi's theorem, which is very instructive. This is stated in terms of the notion of a semi-direct product of two Lie algebras. Okay. Now, what is the semi-direct product? Well, it's composed of two. We already saw that if we have two Lie algebras, then we can form their direct sum. And that's basically the two parts in the direct sum don't talk to each other. The Lie bracket just says that if we were looking at the direct sum, the Lie algebra direct sum of A and B, it would just be the Lie algebra restricts to here, and then these two things are, if I have an element in A and an element of B, its Lie algebra is always 0. They don't talk to each other. It's just a very straightforward decomposition of the Lie algebra. A semi-direct product is something that's a little bit more complicated than that, or a little bit more involved. It produces, so it's a generalization. Somehow the direct sum can be seen as a special case. So what is it? Just like the direct sum, we've got two Lie algebras, but we've got a third piece of information. Namely, we've got a representation of our Lie algebra A on the Lie algebra B, which is to say we have a Lie algebra homomorphism into the derivations on B. Okay. So we're representing the Lie algebra A on the Lie algebra B. We call this representation rho. Then what's underlying it? Well, we should remember that a vector space, the Lie algebra is composed of two parts, a vector space and a Lie bracket. So for the vector space, we just take the direct sum. Nothing changes there, same as for the direct sum of two Lie algebras. But the Lie bracket is different. And I'll leave this as an exercise. That's a good exercise. Is that there's basically a unique way to extend the Lie bracket on A and the Lie bracket on B to a Lie bracket on this direct sum, such that if you have two elements, A and A prime, which live inside in frac A, then the Lie bracket on these guys is just the Lie bracket of A. And similarly for the Lie bracket of B, just as it was in the direct sum case. The difference comes when you have an element A and B and B, then their Lie bracket. For the direct sum, this Lie bracket would be 0. But here we're asking that it's rho of A by B. Okay. So this is now lives inside in the derivations on B, so it can act on B and it produces a new algebra. It produces a new element in B. So when I have two elements, one in A and one in B, and I take their Lie bracket, the Lie product lives inside in B. It goes into B. Similarly, if these were the other way around, of course, if it was BA, then we just get minus this. But it's enough to determine it on AB using the axioms of a Lie algebra. So the part of the exercise, what you need to check here is that this is actually well defined. So it's clear that it actually tells you what the Lie bracket is everywhere. What's not clear is that it's actually well defined. Okay, that's the exercise. But it is. And importantly, as I was saying before, it does generalize the direct sum. So if we take rho to be the 0 representation, then the Lie bracket of A and B will just be 0, which is to say we reduce down to the case of the direct sum of two Lie algebras. So it's a very useful generalization. That it's useful, I guess, because it arises naturally in the theory of Lie algebras everywhere. And this new product, sorry, these should be A and this should be, okay, I've written G and A here when really I should have done the same thing as I had above. I've written A and B, so this is A, and then this is B, and this is A, and this is B. So the semi-direct product, we call this new Lie algebra the semi-direct product. So it's, as I said, it's a generalization of the direct product, but a little bit different. So it's a semi-direct product of A and B, and we denote it by taking the direct sum and putting the symbol for the representation rho down here to warn somebody that it's not a straightforward direct sum, but it's something that's like twisted somehow. Okay, so that's semi-direct products. Why are we interested in them? Well, we're interested in them because of this result, Levi decomposition. So if you remember, we've been dealing throughout with, as I would speak about, two sort of extremes of Lie algebra theory. On one side, You've got nilpotent or more generally solvable Lie algebras. And on the other side, we had semi-simple or reductive Lie algebras. The semi-simple reductive didn't have that many ideals. They decomposed, I guess, into atoms, these like irreducible parts. And they were constructed up from these, so the sort of atomic behavior somehow. But on the other side, for the nilpotent or solvable, they had this series of Lie algebras inside them, so they couldn't take them apart into atoms like this. The thing, that structure property that they had was this series of Lie algebras that lived inside them, and they were somehow at different extremes. So here we finally get like a proper statement of this. And it says that, in fact, for any finite dimensional Lie algebra over a field of characteristic 0, there will always exist a semi-simple subalgebra inside in G, such that for some suitable homomorphism, I guess we won't worry so much about what form this takes. We just go to that it exists. There exists a map from this semi-simple part into the derivations on the radical of G, this maximal solvable ideal. Particularly, it's a solvable Lie algebra, and our Lie algebra G can be decomposed into a semi-direct product of the two of these. That's very nice. So it somehow says that we've been studying the solvable and the semi-simple that we've been studying up until now, that these somehow give you everything, that you can somehow glue together solvable and semi-simple and produce all possible finite dimensional linear algebras over a field of characteristic 0. And that's why we put so much importance, I guess, on trying to understand solvable Lie algebras and trying to understand solvable semi-simple, because they give you everything. So again, a very nice result, a very important result. And what was somehow surprising, though, that you start from this abstract definition of a Lie algebra. And once you assume that your field is algebraically closed and that your Lie algebra is finite dimensional, then you can tell that every time it decomposes into one part semi-simple and one part solvable. And that solvable and semi-simple are fundamental notions when coming to understand Lie algebras. Okay, that's Levi decomposition. It has an analogous, there's an analogous version, for example, for finite dimensional algebras in Wedderburn's theorem. So this is not something that happens in isolation in Lie theory. It's a general phenomenon in algebra, a deep phenomenon. Okay, and the last but not least, the last result we're going to present, another general result. The proof of Otto's theorem is complicated, definitely outside a course like this first course in Lie theory. So we're just going to state it, but it's easy to understand what's going on. It says that every finite dimensional Lie algebra over a field of characteristic 0 admits a faithful, representation is there twice, admits a faithful representation into the general linear group V for some finite dimensional V. So this is definitely a very nice way to finish. It's saying that we introduced this abstract notion of a Lie algebra in the very first lecture. Then we showed that canonical examples come from matrices with commutator brackets or subalgebras of matrices with commutator brackets. And what Otto's theorem says is that basically you can understand any abstract Lie algebra in this sense. Because if it's a faithful representation, that means that it's an injective map from the Lie algebra into GL of V. And it means that it's isomorphic to its image inside there. So basically it's the same Lie algebra, it's the same up to isomorphism. So every Lie algebra can basically be understood. Every Lie algebra can be understood as a sub-Lie algebra of the general linear algebra of a finite dimensional vector space V. Every finite dimensional Lie algebra. So even though we started off with this very abstract definition, it turns out that there actually aren't any examples except sub-Lie algebras of the general linear group of a vector space, any finite dimensional examples, which is great. It's somehow it's surprising initially maybe, but true. So at this point, you might ask, I mean, what's the point? Why then do we bother to define a general notion of a Lie algebra. Why don't we just deal with matrix algebras directly? And in terms of that's it, we may be able to describe them like this, to actually deal with them, just to actually try to develop a whole theory of subalgebras. It turns out it's easier to do it, it's better to do it from the abstract sense, and then show that everything can be realized. I guess the example here to keep in mind is, if you think of finite groups, every finite group can be understood as a subgroup of the symmetric group. But nobody would propose that you just study the symmetric group and forget about abstract group theory. It would be too confusing. So I guess maybe the lesson to think is that the general framework is there in order to help us to understand what's going on. But just to stress again, all finite dimensional Lie algebras are basically realizable inside the general linear group of V, which is also somehow comforting, or it gives you maybe a grasp of, or it gives you a concrete feeling for what Lie algebras are. They are all contained in GLV. Finally, the final point, what does that have to do with the previous result, that everything is going to be a composition of the radical, semi-solvable part and the semi-simple part? Well, if you remember, if our Lie algebra is simple, then the adjoint gives us a representation, a faithful representation inside in the general linear group of the Lie algebra. Okay, because the thing that's killed by the adjoint is going to be the center. If it's simple, it has no center. And then if it's semi-simple, it's a direct sum of all of these things. Remember, we actually were able to identify it with the space of derivations in a previous result. So basically, this theorem here, Ado's theorem for semi-simple, we've already done. We were able to prove this, and it wasn't actually that difficult. But this proves it for general finite dimensional Lie algebras. And one way of proving is through this. So for the semi-simple part, we know that this is true. The trick is to try to extend it up to the solvable part, and then to the whole, and then give you the whole thing. So we can think about Ado's theorem as like as an extension through Levi decomposition of the proof for semi-simple Lie algebras up to all finite dimensional Lie algebras over a field of characteristics theorem. Okay, so with that big result, we'll finish, and the next day we'll move on for the last couple of lectures to the classification of semi-simple Lie algebras. This is where we leave solvable behind. We won't mention it again, and we're going to focus exclusively on semi-simple. And it turns out that we can actually classify these things. It's not true at all for nilpotent, but for semi-simple, we can classify them. It's a very, very beautiful classification. Okay, so thank you for your attention, and see you next time.